So section 10.8 is the last section before we move on to the trigonometry part of the class. So this section is kind of interesting. It's looking at something that you've seen before, which is systems of equations. However, you may not have seen before nonlinear systems. So what about this makes it nonlinear? So see how this first equation is an x squared. So second equation here is a linear equation. So that's a line, but the first one is not. So overall, this is a non-linear system. So my goal is to solve this system. So solutions are x, y pairs that satisfy both equations. Okay, so in order for a solution, or well, let's say it this way, in order for an xy pair to be considered a solution to the system, it has to satisfy not just one, but both of the equations in that system. So if you think about what that means graphically, well, if I have an xy pair that satisfies both equations, then that means that that xy pair, that point, is a point on both graphs. So it would be a point that both graphs have in common. So solutions graphically would be intersection points. Or in other words, points where the two graphs cross, points they have in common. So as far as ideas for how to solve a system of equations, well, one thought would be, what if I just graphed the two equations? Now, for this problem, that's pretty simple to do. So let me graph number one here. That's a parabola, shifted up one. If I plug in 0, I get 1. If I plug in 1, I get 2. If I plug in 2, let's see, I get 4 plus 1 is 5. And then this guy's symmetric over the y-axis. So there's the first graph. Let me graph the line. Okay, so that's a line, y-intercept of 1, slope of 2. So 0, 1, then up 2, right 1, up 2, right 1. Okay, it's gonna look something like that. Okay, so this problem is actually simple enough that I can tell the intersection points just by looking at the graph here. Okay, but the problem with solving these by graphing and looking for intersection points is, well, a lot of the time, if I don't do a really nice job graphing these, I can't tell what the solutions are. Or, of course, if the intersection points are not actually at integer values, so they're not at nice numbers, I wouldn't be able to read those off. However, graphing is a nice thing to do because I can at least tell how many solutions to expect, because I can see here I have 2 intersection points. I know right away I'm going to find 2 solutions. Okay, so what is another idea for solving systems? So one thing you could do is the substitution method. We've done this before. So this is where you solve one of the equations for either x or y, and then substitute that into the other equation. So that's actually a really easy thing to do in this problem because both equations are actually already solved for y. So if I do a substitution, then here aren't I really just setting the two equations equal? So let me see, subtract the 1's and then subtract the 2x. This is quadratic, so I set it to 0. Factor out the x. So my solutions would be 0 and 2. Now remember, solutions are coordinate pairs. So what I know so far is I know my solutions are going to be like 0 something and 2 something. Don't forget I have to get the corresponding y values. So what I have to do is I have to take my solutions and plug those back in to get the matching y. So let's see, if I use 0, then y is 0 plus 1, 1. For 2, 2 squared plus 1 is 5, or if I use the other equation, 2 times 2 plus 1 is also 5, right? So I can see those work in both equations. So this is my answer. These are my answers here. So this is what I would box. That's my solution. Okay, then if I look back up at my graph here, do those look right? Let's see, that looks like 0, 1, and that looks like 2, 5. So indeed, I found my two solutions. Let's try another one. So number 2. Put this down a little bit. Okay, let me try just solving this first. This is another problem where both equations are already solved for y. So my substitution is really just setting the two equations equal. So to solve this, let me try squaring both sides. Now on the right, I actually have to do a FOIL. It's 36, let's see, minus 6, minus 6, minus 12x. Okay, this is quadratic. So set it to 0. So let me rearrange. I'll have x squared minus 13x plus a 36 is 0. Let's see, adds to negative 13, multiplies to positive 36, minus 9 and minus 4. Okay, so my x values look like 9 and 4. So now I set up my pairs, but remember I have to still get the y. Okay, so if I take these values and I plug them in up here, well, let's see, the square root of 4 is 2, the square root of 9 is 3. So it looks like I have two solutions. Let me graph these. Okay, square root of x, 0, 0, 1, 1, 4, 2. Let me even do this. I want more room on this side. Okay, where was I? So let's see, 0, 0, 1, 1, 4, 2, 9, 3, etc. Okay, now let me look at y equals 6 minus x. Isn't that the same as negative x plus 6? That's a line, right? The y-intercept is 6. The slope is -1. All right, so looking at the graphs, I can tell immediately how many solutions I should have. I should have one solution. Okay, so something is wrong here, so the correct solution would be 4, 2. Okay, so how would I have known algebraically that this guy, 9, 3, is extraneous? Well, the thing is that, remember that solution has to satisfy both equations. So if I plug that in here, let's see. Square root of 9 is 3, looks good. But 6 minus 9 is -3, not 3. So you see how the second equation is actually not satisfied. Versus with 4, 2, the square root of 4 is 2, 6 minus 4 is also 2. See how both equations are satisfied? So because both equations are not satisfied, that tells me algebraically, even if I wasn't going to graph it, that 9, 3 is not a solution. So I need to make sure I cross that off and indicate that 4, 2 is the only valid solution. More room. All right, what about this one? Okay, so here's one where both equations are not solved for y. So it's actually not particularly easy to isolate x or y. So one thought is, well, what if I try the other method? So instead of doing a substitution, what if I try elimination / addition method? Okay, so the goal with that method is to add the two equations together in a clever way so one variable cancels, or one variable is eliminated. Okay, so if I was to just take the original setup here, and I was to just add, that's what I wanted, if I was to just add the equations together, as they are, well, it wouldn't work because nothing would cancel. See how this is what I would get? I mean, it's true, but doesn't help me any. So a lot of the time you have to do some sort of preliminary step, like multiply one or both of the equations by something on both sides. Okay, so that when you add the two equations together, you get a cancellation. So what if I multiply, say, the top equation by -1? So I'm multiplying everything on both sides there. So I didn't actually change the equation. But now, when I add these two together, see how those cancel, those cancel? So all I'm left with is this equation. So that's really easy. I can tell that the y is 4. I lost a negative. Should be -16. Y is -4. So in this case, the first thing I've solved for is the y. So I have to still get the matching x. And to do that, I plug this y value in. I should be able to plug that in either equation and get the same result. If I try the top one there, x squared plus negative 4 squared is 16. X is 0. So there's my solution. Okay, so I wanted to show you a few other things with this one. This is kind of an interesting one. And I still need more room. Let me move all of this again. Okay, deal with that later. So what if I would have wanted to do this one by substitution? Can. But I would not solve for like, so if I was to solve for x, look, I mean, I'd have to do this and then take the square root, plus or minus, and then I can't simplify that. Then I have to plug that whole mess in down here. That's not going to work out very well. So what if I don't solve for x or y, but I solve for something else? Like what if I solve the top equation for x squared? What if I take that and I substitute that in for x squared here? Then I have 16 minus y squared plus y squared plus 4y is 0. Then look at that. These cancel. And we're back where we were before. So that's a thought. There's something else I was even thinking. Look at this. What if I do this? This is kind of clever. X squared plus y squared is equal to 16. What if I substitute that in here? In other words, wouldn't that just leave me 16 plus 4y equals 0 immediately? That's kind of cool. So to use substitution, we don't always need to solve for x or y directly. You could solve for something else. X squared, say, depending on what the equations look like. Okay, so we have our solution. What we haven't looked at is actually doing the graphing part. Let me move this. See if I can do that. Okay, that'll work. Actually, let's do this instead. This will be easier. Let's use this one. And let's move this down again. All right, so my goal is to still, well, we haven't actually looked at the graphing part. So what were my equations here again? So let me see if I can come up with the graphs of those. So do you remember what this guy is? So that's an x squared plus y squared equals r squared. That's a circle centered at the origin with a radius r. That's easy, huh? it's a circle centered at the origin. The radius is 4. So I'm going to graph that. Going to have, let's see, 1, 2, 3, 4 up, 1, 2, 3, 4 left. Try to make it look like a circle. Actually, surprisingly hard to draw on here. All right, that's good enough. So what about the second one here? Well, actually, this is still an x squared plus y squared, as in I still have the same coefficients on x squared and y squared. I have a plus in the middle. This is a circle. If I had different coefficients, this would be an ellipse. So what does this linear term here do? This shifts the circle. So this is a circle, but it's no longer centered at the origin. Okay? So this guy is a shifted circle. So the standard form equation for a shifted circle, if you remember, looks like this. The center is HK, and the radius is R again. So what I have to do is I have to take that second circle there, and I have to put it in standard form. And the way we put the equation in that standard form, we use a process we've used before, completing the square. Okay. So if you remember the steps, let's see. Move the constant to the other side. There's no constant. Divide, if there's like a 2 or something here, I'd have to divide the whole equation by 2. None of those things, so I go ahead and find my special number. Remember what that was. B over 2 squared. So look, in this case, I'm completing the square for y. So that would be 2 squared is 4. And so I add that on both sides. Now I'll add that next to the y, since that's what I'm interested in. And then I just go ahead and factor, and then I'm done. So you see the x is done, because x squared is x minus 0 squared. So there's that circle written in standard form. So its center, 0, -2, and its radius is 2. Okay, should I graph that one in blue? So its center is here. Radius is 2. So starting at that center, okay, and so I can see indeed I have that one intersection point, which is 0, -4, which is the solution that we found up here back when we solved the system. So there are really two different things we're doing in this problem, right? We're solving the system, that's what we did here, or you could do it by substitution. And then we're creating the graph. To do that, I had to actually put the circles in standard form so I could read off the information that he needed. Okay, so what about something like this? So I don't really want to graph this in detail. I'm just kind of curious what I'm dealing with. So this guy have a sum of x squared and y squared, different coefficients. I have an ellipse. Like I said, I'm not graphing this in any detail. Okay, let's see, the second one, it's a linear equation. This is a line. Just kind of really rough scratch work. Plus 3. So I don't know, looks like something like that to me. So let's see how we do. I'm anticipating I'll find 2 intersection points. Let's see how we do. So, So you see, I don't see like terms. Like in order to use elimination, see how this is x squared and this is x? Nothing's going to cancel. Y squared and y, nothing's going to cancel. So I don't have like terms in both equations. So that leads me to think I'm going to do a substitution. So let me solve the bottom equation for, say, x. And then let me substitute that in here. Guess that's a FOIL. So I don't know what the numbers are going to come out like here. Let's see, I guess all 3 of these terms are divisible by 9. That might work out nice then. So 4y squared minus 6y, let's see, minus 4. Divide by 2. Factor. Let's see, is it minus 2 and plus 1? 2y squared minus 4 plus 1 minus, looks like it. Okay, so now I have my pairs, but I have to find the corresponding x's. Okay, so if I pick one of these equations, that one say, let's see, so I'll have, if I use the y equals -1/2, x plus 3/2, -9. So subtract, so -18/2 minus 3/2, that -21/2. And what about for the x or for the y equals 2? Be x x minus 3 times 2 is negative 9. Negative 3. Okay, let me see. So let's see. If I got my signs right, I've got negative and negative, that'd be this one. Negative and positive, that'd be this one. So it looks like it to me, like I said, it didn't do a fancy graph, but it looks like I have the solutions at least in the correct quadrants. Just looking to see about doing one more example for you. Let's try one more. So you know what, I'm just gonna skip that guy there for the moment. We'll go back to that guy. So what number will this one be? I want to do one more. I'll call this one number 5. And then we'll do that word problem at the end. Let's see what this one comes out like. About something like xy is 24, 2x squared minus y squared plus 4 is 0. So again, I don't actually have like terms, so I would do a substitution. So if I solve the top equation, or say y, that's going to be 24 divided by x. Then I'm going to substitute that in, so I'll have 2x squared. And then I'll have 24 divided by x squared. So now I need to square the top and the bottom. So the numbers might be a little bit big, but that's okay. So now I'd like to get rid of that fraction. So what I'm going to do is I'm going to multiply both sides of the equation by that x squared. Because actually what I have here, I actually have an equation that's quadratic in form. See how this looks like a quadratic equation? It's just that I have that higher power of that 4 instead of a 2. I divide by 2. What's half of that? 250 and another 38. 288. Like I said, the numbers are a little bit big. That's okay. So now I can factor this, but I'm factoring it in x squared. Now, if you can't figure out the factors, I guess you could always use the quadratic formula. But I'm kind of looking, let me see if I can figure this out. So my numbers have to multiply to 288. So 288 in 1, be 144 in 2, I guess that'd be 72 and 4. So 36 and 8. I'm looking for, I need to add to a 2 here. So, oh, look at that. What about 18 and 16 then? So will that work? Plus 18 minus 16? That looks like that would work. So x squared cannot be negative. So it must be that x is plus or minus 4. So now I have my x's. Let's get my y's. So I think this would be the simplest equation to use. I know y is equal to 24 over x. So if x is, say, negative 4, y would be negative 6. And if x is positive 4, y would be 6. Okay, so looks like I have 2 solutions. Let me just think about the graphs for 1 second here. So I didn't draw a graph yet. Kind of curious what I'm dealing with. And I bet you I can figure that out actually pretty easily. Sure. I'm kind of curious here, so let me see if I can come up with a graph. It can even be kind of a rough sketch. Let's see what we're dealing with. So the first equation is a 24 over x. So that's a 24 times a 1 over x. Remember what a 1 over x looks like? So it's like that, but with a vertical stretch. So if I plugged 1 in here, I would get 24, right? So I mean, I'm not going to be able to do this to scale. How about I'll label? If I plugged 2 in there, I'd get 12, somewhere here. If I plugged 4 in there, I'll get 6. Something like that. Higher, and we'll just label it. Okay, so I mean, this is a reciprocal function, but stretched. Okay, now this is symmetric. So I'd have negative 1, negative 24, etc. Rough sketch. What about this equation? So this guy, let's see. This is a hyperbola. Because isn't that, let's see, if I divide by 2, now we don't like to have a negative number here. Let me multiply both sides by a negative. So actually this is the hyperbola I'm dealing with. So this is a vertical hyperbola. The y-intercepts would be plus minus root 2. That's like 1.4-ish. Not to scale. Trying to get a rough idea. Okay, then we put, you know, the asymptotes on there, etc. But roughly, I mean, just to know how many intersection points and in which quadrants. It's gonna look something like that and like that. So even just with that information, I can see, I don't think that's actually at the at 4, 6, but I can see I'm going to have an intersection point in quadrant 1, so should be a positive, positive, and in quadrant 3 should be a negative, negative. So what the heck did I find? Oh, look at that. Oh, look at it, it is at 4, 6. That's cool. So I found a positive, positive, and a negative, negative. And so my solutions look good. Now what happened to that word problem? That's the last one, and I kept moving it. Let's put it down here for once and for all. Okay, a rectangle has a diagonal that measures square root of 13. Okay. The area of the rectangle is 6 square feet. Find the length and the width. Okay, so I know a couple things. I can use the Pythagorean theorem. Length squared plus width squared equals hypotenuse squared. I know the area of a rectangle is the length times the width. That would be 6. So here's my little system. Okay, so let's see, I have L squared plus W squared is 13. I think I would solve the bottom equation for L or W. Substitute. This looks similar to the last problem. So square the top and the bottom. The numbers are nicer here. Multiply by L squared. Okay, minus 9 and minus 4. So positive 2 or positive 3. These can't be negative, right? Because these are lengths. So when I go back up to solve for W, well, W is 6 over L. So if L is 2, 6 over 2 is 3. If L is 3, 6 over 3 is 2. So you see how no matter how I cut it, one side is 2 and one is 3, right? That's because I can rotate the rectangle. So my solutions are, the rectangle is 2 by 3 feet. Or you can say 3 by 2. It doesn't matter.